Now, the first topic we're going to be covering here in today's webinar is the role of tolerances and stock parameters. So first, let's talk about how tolerances will affect your machining, especially in 2.5 axis operations. So tolerance defines or is basically the deviation from your actual geometry. So as you can see from these images on the slide, the slacker the tolerance, the more deviation you will see from your actual part region or geometry, and slacker the tolerance will also have larger chord segments. So the tighter tolerances, as you go tighter, the chord segments will be much smaller and it will be within the deviation of the tolerance that you specify. Now these affect more when you're using toolpaths outputting as linear segments, when you're working with like polylines or splines. When arcs are not being fit to your toolpaths, the tolerance you can see here has more effect in, as you can see there, there's more deviation from your part geometry. Now, you can fit arcs to your toolpaths. Arcs are automatically fit to arcs and circles when you're working with arcs and circles in your geometries. By default, if you have output arcs as linear segments not checked, arcs are fit to the toolpaths. And we'll talk about how the arc fitting tolerance will affect for polylines or polycurves or splines as I go through an example with you. So I'm going to go ahead and switch over to one of our CAM plugin products. In this case, in this example, I'll start with Rhino CAM. We'll also talk about this in our other products as well, as time permits. Okay, so we covered this particular part programming in our previous webinar. So I'm going to use this as an example to cover the tolerances and how it affects in toolpaths. I'm going to switch over to a top view here, and I'm going to be focusing on tolerance in this pocket region. I'll display the toolpath. I have created a pocket operation and left the tolerance as 10 thousandths. And as you notice, in these areas with linear motions, with arcs not being fitted to the toolpath, you can see how the tolerance affects around the pocket boundaries as you're programming the pocket, as well as around these island regions. So slacker the tolerance, you'll notice more deviation from the part geometry. So if you want to keep it as tight or closer to the part geometry, you would want to consider tightening up the tolerance. So the next example here I have is where the tolerance is tightened up to 1,000. So tightening it up to 1,000, well, you can see that there's smaller facets and much tighter, much closer within the tolerance of the part region of the geometry for both the pocket boundary as well as the island region. Now the same goes with other two.
Let me interrupt here. That was a really good question about the size of the parts that you have. So because that does play into the tolerance settings. So if you can talk a little bit about the size in your slide as well as the parts, that'll be good.
Sure. Thank you. So in this particular example, the part I'm working with is about a little over 7.5 inches by 4.5 inches in X and Y. And the cutter used for these, the tool uses about a 1/2 inch end mill. So also the smaller the part you're working with, the tighter the accuracy, the tighter tolerance will basically maintain it within the deviation from the part geometry as well. Now let's look at how fitting arcs to toolpath will affect the tolerance. So I'm going to go ahead and make a copy of one of these pocket operations here, copy paste. I'm going to go into the preferences, go to machining, and make sure output arcs as linear segments is not selected. And I'll regenerate the pocket operation. And you'll notice that arcs are being fit automatically to the toolpath where you have arcs on the drive or the part region along the model. Now, additionally, you could fit arcs to your toolpaths when you have polylines or splines, and this can be done by going to the advanced cut parameters. you have the option to perform arc fitting and specify the tolerance for arc fitting. Ideally, we recommend setting the fitting tolerance to be set to 2 times of what you set under the tolerance for global parameters. So in this particular example, I'm going to change this to 0.002, which would be 2 times of the global tolerance, and then generate. So this will give you the best result for arc fitting, so where splines or polylines are fit to arcs wherever it's feasible. And the reason we recommend 2 times is to avoid tolerance stacking. So arcs can be fit to toolpaths, and you can specify the arc fitting tolerance. So this gives you an overview of how tolerance affects your machining in 2-axis operation.
I want to jump in here, Uday, and talk a little bit about tolerance stacking. You mentioned that, but I want to dive in a little bit deeper there. One of the things when we do arc fitting, we are actually fitting arcs to the toolpath points. So, I mean, we are looking at just the toolpath and fitting the arc geometry to it. And obviously, when we do that, we have to use a particular tolerance to do it. So this tolerance is independent of your machining tolerance. So in some cases, it might actually introduce some errors because we are using an additional tolerance on top of your machining tolerance. But if you're machining an arc, it's possible that our arc fitting will give you an exact arc. But in some other cases, let's say you're using a NURBS curve, you're machining a NURBS curve, and we fit an arc to the resulting toolpath, that might result in a little bit of an error. So you got to be a little bit careful about these tolerance stacking, what we call tolerance stacking, because you have a machining tolerance. On top of that, you have the arc fitting tolerance. So I hope that makes sense. Thank you.
Thank you, Joe. The next topic we would be covering here is the stock parameters and how this affects in machining in 2.5-axis operation.
Okay, sorry, I want to stop you again because there are a couple of questions about what are the disadvantages of using very tight tolerances. You can explain that.
Sure. So if you're using a very tight tolerance, one of the things you'll notice is you'll have more number of go-to motions. If there are several linear, if the toolpath is being output as linear motions, you'd end up with more number of point-to-point moves. So it could be possible on some machines or controllers, the control may not have enough look ahead, and you might see the machine probably could cause stuttering or slowing things down. So as you set the tolerance in this particular example, I'm going to go to the information tab, and you will notice that in the first case, when I set the tolerance to 10 thou, the number of go-to motions is at 607, basically the number of point-to-point moves. And when we tighten up the tolerance to 1 thou, you can see it's almost 2.5 times. We have about 1557 go-to motions. And the last one here you're seeing is the arcs being fit to the toolpath. So with the tighter tolerance and it arc fitting, you're seeing about the number of motions is about 2 times. And fitting arcs to toolpaths makes it also smoother and easier on the machine to work with. So tighter tolerance, the more number of go-to motions and more lines of code, which results in more lines of code in your posted G-code or output file. I hope that answered your question, sir. So the next topic I will be covering here is going to be how the stock parameters affect in 2.5-axis machining. So I'm going to switch over to the slide first so we can talk about the role of stock parameters. So stock in 2.5-axis machining or 2-axis machining is a wall stock or an XY stock. So in this particular slide, as you're noticing here, it shows the amount of material you'd like to leave or stay away from the side walls. In 2-axis machining or 2.5-axis milling, we do not specify a floor stock because the Z, the total depth is controlled in your cut levels as you specify the depth per cut and the total cut depth. Well, the stock, what parameters, what you specify in the global parameters are the amount of stock you would like to leave in X and Y or stay away from the side walls. So in this example, we have a pocket operation. So the default parameters on pocketing or facing operations in any of our machining operation dialog in 2-axis, it specifies a stock to leave of about 25 thousandths if you're working in inch units or 0.6 millimeters if you're working in metric units. So I'm going to go ahead and switch to RhinoCam, and we'll take a look at the stock parameters and how this affects our toolpath. So if I take a look at the pocket operation here, under cut parameters, you'll find global parameters, and this is what we call the stock to leave. And by default, it's set to 25 thousandths because pocketing operation is considered like a roughing operation where typically you would intend to leave some stock so you can go back and finish this with a profiling operation. So when we specify a stock to leave, the toolpath, the last path here, as you see, it stays away from the finished edge of the pocket boundary by the distance on all the sides. So let's run a simulation in here and we can visualize it. I'll toggle off the toolpath visibility while it's running the simulation, and also display the part visibility in here. So you can tell by looking at it. So the part region is visible. It's highlighted here. And as you can tell here, we have left 25,000 stock all around the part. So specifying a positive value for the stock will make the resulting pocket cut to a smaller size. If you specify a negative stock offset, it'll overcut the pocket boundary. So going back to the global parameters under cut parameters tab, specifying a stock of minus 0.025 will overcut it. So if you have an application or a need to overcut it, you can specify a negative stock offset and that'll overcut it. The same goes with all 2.5 axis operations, pocketing, profiling, and other methods as well. So in this particular example, you can see that we are overcutting it. I have the part model visible. I can toggle the visibility so you can see the difference here. Now we are overcutting it by 25 thousandths. Now setting the stock to leave to 0 will finish it right to the edge of your pocket. So there's the pocket boundary and the resulting toolpath is right to the edge of the pocket. And the same goes with island regions as well. So if you specify the stock to leave, you would leave material around the island. Or if you specify to put a negative stock, it'll overcut it even on the island region as well.